And there we go. All right. Oh, beginning chapter three on orbits and gravity. We're talking about orbital motion, and the force of gravity. So our first section of these slides is all about someone named Johannes Kepler. And we have some laws named after this scientist. So if you recall at the end of lecture two, we wrapped up by looking at a timeline that took us from the ancient astronomer Ptolemy and his incorrect geocentric model of the solar system right up to Nicholas Copernicus, his correct heliocentric or sun-centered model of the solar system, and how that led to the discoveries and confirmation of that heliocentric model by Galileo. So that's where we're going to pick things up, and we're going to talk about what happens around this time by another scientist. Okay. So, right coinciding with Galileo's lifespan, who was born in 1564 and died in 1642, um, and published his findings about the moons of Jupiter and the phases of Venus, and his support for the heliocentric model of for which he was excommunicated from the Catholic Church. Um, so that happened kind of in his middle life, and then he continued to work late into his life. But you can see he lived quite a long time. And so there's this other name now that's just popped up, and we see the picture of him here in yellow. This is someone named Tycho Brahe, and I said other scientists. Tycho Brahe wouldn't really be considered a scientist. He was a observational astronomer, and I don't mean to speak badly of him, but he didn't really use the scientific method. But he was very meticulous in taking observations of stars. So he was throughout much of his life, took very careful and detailed measurements of the locations of stars and the locations of planets relative to those stars. He had an observatory at his home. He was part of a kind of wealthy elite class, and lived a life of leisure essentially, and was able to do this with much of his time. What's almost most important about him is who he hired as an assistant. Okay. Because he hired Johannes Kepler to help him with his hobby of astronomy, and, also maybe obsession and passion of astronomy. And unlike Tycho Brahe, who was part of this wealthy elite class, Johannes Kepler was not. He came from a working class family in uh, Central Europe, kind of like Copernicus, from that same region of what is now modern day Netherlands or Holland. And he took the findings of Tycho Brahe, mostly after Tycho Brahe's death in 1601, and used them to develop a theory. So, like a lot of scientific endeavors, you have like a data set, you have a set of observations, of values, and you take them and you work with them. You make calculations, you build a model from those values. Today, we do that largely, with computers. Sure, there's lots of human input and human ingenuity, but we're putting ideas in, or we're making calculations with either calculators or computers. Of course, Johannes Kepler, working in the early 1600s, first half of the 17th century, he would have been doing everything by hand, right? I mean, this is predates so much of what we know about modern mathematics. In fact, it's even before a lot of the foundations of modern mathematics. But he was drawing out these ideas using lots of straight edges, to actually make geometric explanations of a lot of these calculations and was able to come up with some really insightful conclusions and ones that have really remained relevant and accurate up till the modern day. Okay? And those have been distilled down into three laws. So when we talk about Kepler, besides this historical background, what we want to remember are his three laws. Named after him, Kepler's three laws. All right. This was his publication, which kind of codified those three laws. All right. And this was the observation from Galileo, which we mentioned before, the observed phases of Venus. All right. Which is, again, confirmation of Copernicus's model. Okay. So Kepler's work. Notice here that we have kind of a example of a mock data set that he would have been working with in terms of different dates and the exact values of declination and right ascension of the sun and Mars. All right. And so then he was able to, as I mentioned, use geometric positioning. Right. So he's like, put out these points almost like plotting them on graph paper, and was able to show the path of Mars. See? Because notice that each time we have the sun fixed in place over, not quite, obviously it's following the ecliptic, but not moving if you only looked at the relative motion of Mars. So notice that the numbers here are changing for the sun, but we don't see any movement of the sun. Well, because we could subtract that out. So if we said, okay, well, we only want the relative motion of Mars relative, or at least like relative to the sun. So instead, this is showing, relative motion of the sun and Mars to Earth. What if we are only interested in the relative motion of Mars to the sun? Well, by doing some simple arithmetic, we could get that positioning of Mars relative to the sun, and that's what these red dots represent. Sort of the difference between the values for the first row, second row, third, and fourth. And then extrapolating for all of them, or imagine that we've plotted all of them, we now have, by just observing the position in the night sky of the sun and Mars on subsequent days, we now have a path, an orbit. We have an orbit of Mars around the sun. And what shape do we see? What is the shape of this orbit?
Like an oval.
Like an oval, exactly. Yep. Yeah, and calling it an ellipse, um, fiore, sorry if I mispronounced it, is actually totally accurate, and that's the more technical term. But although ovals, you might maybe kind of have a different definition than ellipse, they're used interchangeably. So I find both totally acceptable, as do the authors of these slides. So oval, ellipse, whatever you want to call it, not quite a circle, right? An elongated circle. And let's see, I'm going to wrap stuff up, but I want to get to a good stopping point. Let's see. Okay. It's definitely not a circle, right? It does not round enough. And that was basically the key finding. There's a famous quote, this last thing I'll say before we take our break, where in his writings, Kepler points out, and this kind of course, is translated into English. He originally wrote it in either Latin or German, I'm not sure, and probably Latin. And and he was like talking about how he was led to this inevitable conclusion that the orbits had to be ellipses, even though he had no bias, he had no assumption, and in fact, he had a lot of hesitation to suggest that the orbits were elliptical. He couldn't deny it. He just took more and more careful, calculations off these already very detailed and many years worth of observations, right, taken by Tycho Brahe, and there was just no other conclusion he could come to. And that was the foundation of our understanding of planetary motion, at least a more accurate understanding. All right. So we'll pick up on that idea after a 5 minute break. So let's plan on coming back at 11:23 for the rest of this chapter. Okay, so continuing with Kepler's laws, getting into them officially. Okay, so no surprise, we're starting with the first law. So Kepler's first law is what we were just talking about those findings, noticing that the path of Mars around the sun was not a circle, is that planets orbit in ellipses. That's it. That's that's basically the law. But the full statement continues, and their star, in the case of planets in our solar system, that star is the sun, is at one focus. Okay? That does demand the question, what is a focus? I'll clarify that in just a moment. Okay? This is also true for any other orbit. So it's true for moons that orbit planets. In that case, the planet would be at one focus. A comet that orbits a star, like the comets that orbit our sun, they have the sun at the focus of their elliptical orbit. Asteroids that orbit the sun, or sometimes you actually have asteroids that orbit other asteroids. It's a pretty common occurrence. You can also have an asteroid that orbits a dwarf planet. All right. But in that case, it would be called a moon. So once an asteroid orbits any type of planet, including a full planet or a dwarf planet, it's classified as a moon. Not that, you would lose points for getting that little detail wrong. That's the official way it works. Okay. So always elliptical, always has the body that's being orbited at one focus. With the orbit around the sun, there are two special terms that refer to points in the orbit, in the elliptical orbit. And in the example shown here in this slide, we have what would be considered a highly elliptical orbit. When you say it's highly elliptical, you mean that it's not very circular, because a circle is a type of ellipse. It's just a special type. And a circle is a type of ellipse that has no eccentricity. And so when you have a really high eccentricity, which is really, highly elliptical or highly eccentric, both terms are used, then you have this real oblong appearance, the stretched out appearance that we see here. And like, to reiterate that fact, none of the planets would have an orbit that looks this dramatically elliptical. So like they're all much closer to circles. As you get further out and you look at, the orbit of Pluto, that one noticeably elliptical to, just like looking at it in a figure, but even then closer to a circle, certainly closer to a circle than this figure. Of the actual planets, Mercury has the most elliptical orbit, but still would, look closer to a circle. An orbit like this would be the orbit of a comet, to have such a very stretched out orbit. Okay, but back to the terms. So we have these two terms. When the object is closest to the sun, it's called perihelion. And when the object, like a planet, right, is furthest from the sun, it's called aphelion. So like PH with an F. You can also say aphelion. Both are acceptable pronunciations. Aphelion or aphelion. And I checked that. It's actually both are acceptable. Okay. Um, the reason that I say those terms are specific to the sun, especially because we were just talking about how orbits around moons would also be elliptical, or orbits of moons around planets, is because the names themselves actually refer to the sun. Because notice that there's the letters HEL or helion Well, that comes from the root of the word helos or helios, which is this Greek word for sun. And so it's actually in the word. And there are different terms that refer to the closest and furthest points of orbits around other bodies. Like for the moon, it's like perigee and apogee are the terms. But don't worry about them for now. We just care about these sun specific terms. Okay. Now, I mentioned the focus. What is the focus? Well, maybe some of you have seen ellipses before. Sometimes it gets covered in, like in a math class, geometry, or like high school science of some sort. Like I remember drawing an ellipse by sticking a pin onto like a board, having a fixed amount of string, and then you would, or two pins into a board, and then using a fixed amount of string to like trace out the shape of an ellipse. If that sounds like a familiar activity that you would have done as a child, that's great. But I have, by asking a lot of students, not a lot of people remember doing that. Maybe it's not as popular. But anyway, when you have an ellipse, there's always two foci, which is just the plural of focus. There's always two. Okay. For planetary motion, we only care about one. So we always just say one focus. But in a mathematical sense, there's always two. Okay. And the distance between the foci determines the eccentricity of the ellipse, a term I mentioned before, and that value or quantity, which is zero for a circle. Okay. So the further distance between foci, the more elliptical. And the distance between the foci, so the distance from one focus to any point along the perimeter of the ellipse, and then back to the second focus is always the same. So the sum of these two straight red lines is always the same. So if I was to move along the perimeter of the ellipse, it would always be the same sum. Obviously, the individual lengths would change, but they would always sum to the same. That's why you can use a piece of string and two tacks to hold the string in place and just keep the string taut with a pencil and trace out an ellipse. Here's another example with the green lines, right? Two different lengths, but their sum would be the same as the sum of the two red lines, right? Here we have an example where it'd be straight over to one side, still the same, all right? Okay. So that's basically how the foci determine the ellipse, because they really do. They set the shape of the ellipse. The distance between them completely determines the shape, because you can like map it out from there by having that you know that piece of string. So I guess it's not just it's the distance between them plus the distance that you give, like how much string you give if you're literally making it with string. So it's also set on some sort of parameter of how big you want the ellipse to be. So it's like the distance between the foci and then how far from the foci to the edge determines all the quantities about the ellipse. So there's I'm trying to hint at here is there's some sort of like simple way to mathematically define the ellipse. And to start doing that, we introduce a couple of definitions about the ellipse. We already have, right? We've already defined that there's these 2 points called the foci, right? So two, one focus, second focus. Well, there's also the semi-major axis. And the semi-major axis is half of the full axis along the longer side of the ellipse. And that's usually why when we're introducing ellipses, we show these ones that are really dramatic, because that way we can really clearly see which is the major axis and which is the minor axis. And so the major axis is always just the longer of the two sides of the ellipse. And the reason it's the semi-major axis is because it's half of it, in the same way that the radius is half the diameter. So that's all we mean by semi. So here's the semi-minor axis, which is just half of the axis that's shorter. The focus distance is the distance from the center, which is the intercept or where the two axes overlap. So the distance from that intersecting or overlapping point, the center, to one of the foci is called the focus distance. Right? So if you define the semi-major axis, you define the semi-minor axis, and you define that focus distance, now you actually have defined everything that you need to have a unique ellipse. So these three values would produce a unique ellipse in every case. The eccentricity is a measure of how far from a circle your ellipse is. So the higher the eccentricity, all right, then the greater, the stretch of the ellipse. And it's just defined as the ratio or the fraction of focus distance over semi-major axis. So if the focus distance becomes a significant portion of the semi-major axis, you have a very eccentric ellipse. On the other hand, if the focus distance is tiny compared to the semi-major axis, then you have an ellipse that's nearly circular. And that would give you a very small eccentricity value. And by small, we mean close to zero. And here's the example. So if the eccentricity is exactly equal to zero, that is a circle. Still technically considered an ellipse and just a special case of an ellipse. But for all practical purposes, we just call it a circle. Okay? So it's zero eccentricity. And that's because the focus distance is exactly zero. In other words, the circle has the two foci right on top of each other, which then just become a single focus. And we call it the center of the circle. See? So it's like when you turn a circle into an ellipse, it's like you take that center and it splits into two, and then those two foci start pulling apart from each other. All right. If you have an ellipse that's become so elliptical that the distance between the foci has, reached the edges, well, then it approaches a straight line because you stretched it out infinitely and it's no longer an ellipse. Now, there's no orbit like that, but that's like the limiting case. So, as an ellipse becomes more and more eccentric, it approaches a straight line. And in between are ovals. So any value between 0 and 1. Okay? So that's all of the orbits that we're going to talk about have eccentricities between 0 and 1. And usually closer to 0. So, like 0.1 or 0.2 would be fairly elliptical. All right? So here are some pictures of cases. Here is an eccentricity of 0, so a perfect circle. Right? This is what it looks like when the eccentricity is 0.5. See? So even at 0.5, right, it doesn't look that stretched out. Okay? But this is an eccentricity of 0.5, half the way to the maximum possible eccentricity. So it's, the effect of the eccentricity becomes more dramatic kind of suddenly at greater values. Right? So once we get to 0.75, right, it's very noticeably eccentric. Right? There's 0.95. This would be like some comets that only come back to the inner solar system every few thousand years. They can have these incredibly eccentric elliptical orbits. Right. So here we have 0.99. Definitely not a straight line yet, but you could just keep adding nines. So you get 0.999 and 0.9999 and so on. All right. So here are some actual values for planets in our solar system. Mercury, as I mentioned, has the most eccentric orbit of any planet with 0.205. Pluto is included here because, of course, it was once considered a planet. Now it is not. It is now just, a reference as a kind of a representative of other dwarf planets because there are plenty more. Pluto's just the best known. And like a lot of dwarf planets, it has a eccentric orbit. And also like a lot of bodies in the distant solar system, ideas that we'll come back to when we talk about trends in the solar system in later chapters. It's oh, even though is that trend and orbits become more eccentric as you move out past Neptune, it's still not that much more eccentric than Mercury. The other thing to note is that many of the planets have very low eccentricity. So, right, really, except for Mercury, we have all have eccentricity values that are less than zero point 0.1. Okay. In some cases, like Venus, almost a perfect circle. All right. So I remember actually not understanding the question. So, which is a perfect circle? Other is the orbit of Pluto. Pluto, perfect circle. Perfect circle. Well, I apologize. I thought maybe it would come to me when I looked at it. I was looking at these slides ahead of time. And I was thinking, oh, maybe it'll make sense when I'm going over them. But I'm not sure what it's asking. Hmm. Pluto obviously is not a perfect circle, as I mentioned, because it has, and Venus is the closest. Anyway, moving on. Okay, so if you were to have the semi-major axis be 1 mile. So imagine like if you were to model all of these orbits and like take like Earth's orbit and say that our semi-major axis is 1 mile, and you had that like set up in a park or something, then the semi-minor axis, how much shorter would it be, right? Because that might help us be able to kind of visualize what the difference is. Well, for Earth, it would just be 8 inches shorter. I mean, what is 8 inches from a mile, right? A mile is over 5,000 feet. So a difference of 8 inches, less than 1 foot, means a difference of less, right? You know, less than, that 5,000th of, you know, the overall length. So really, really small difference in terms of, the distance from the sun. Okay. So we got, difference of 23 feet from Mars and so on. Okay. I'm going to double check that value for Earth. I think Earth should be feet. Because if you look at it, yeah, I think it should be. Because it's not that much smaller. Or I mean it's not that little of a difference. Think of that should be feet. I can easily do the calculations, but I won't slow us down with it right now. Because Venus is tiny. But there's no reason, right? If you look at the eccentricity of Earth compared to Mars, yeah, it's less. But yeah, I'm pretty sure this should be feet. So it should be 8 feet less, not 8 inches less. Still, right? A tiny amount compared to 5,000. But and that the other reason that I'm pretty sure about that is that when we talk about Earth's distance from the sun, the way that I often remember it and paraphrase it for my students is I say that when we are at perihelion, that's the point where we're closest to the sun. We're 4 million kilometers closer than when we are at aphelion. Okay, so that's a difference of 4 million kilometers between perihelion and aphelion, which is not the same as the difference between the not exactly between the semi-major. They're related, but if that's 4 million kilometers and 4 million is out of an astronomical unit, which I'd forgive you for forgetting, but if any of you remember, that's awesome. Astronomical unit. Well, I got another question coming up, but does anyone remember how many kilometers are in an astronomical unit? In millions? It was one of those two important values you saw in chapter one, the light year being the other one. Yeah. So 149.6 million, we can round that to 150. By the way, thank you, Ace. So if the distance between Earth and the sun, the average distance is 150 million, and we're 4 million kilometers closer at perihelion, the time when we're closest to the sun, versus when we're at aphelion. Well, that type of like proportion, like 4 out of 150, is going to be, like that's the type of difference I think that would match better between semi-major axis and semi-minor axis and 8 feet, versus 5,000 feet. Okay. It's like it's on that same order of magnitude, if you will. I'll try to remember to do that to double check that that is in fact a typo. It's on my to-do list. First, I got to fix the zeros in the grade book and respond to messages. Anyway, carrying on. Okay, so let's check your understanding. Planets orbit in ellipses, and their star is at one focus. What is at the other focus? I didn't explicitly said this, but what is your best guess? Not a black hole. That would be cool. Anybody else? Okay. A lot of votes for four, one for two, and then one for the black hole. Oh, and a Lagrange point, which are interesting, but I'll tell you, it's not the Lagrange point. It is nothing special, which might have seemed like it's a strange answer. Why is it nothing special? It's just empty, okay? And that's the reason I'm asking you is because that's really not what most people think. And so I'm not surprised that it wasn't a very popular answer. It seems too counterintuitive, right? Why is there just nothing at the other focus? Well, that's just the way gravity works. The 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 gravitational attractor, the thing that's being orbited around, in the case of Earth and the sun, it's it's located at one of the two foci. It doesn't matter which one, and that's it. Nothing's located at the other one. Okay, so and it wouldn't be the moon because of the scales involved. When you think about orbits, they're much, much larger, the planetary orbits, than any moon orbit. So the distance between Earth and the moon is tiny compared to the distance between Earth and the sun. I'll throw out the numbers, but you're not responsible for them just yet. The distance between Earth and the sun, obviously, one astronomical unit. That one you should start to be getting into your head, 150 million kilometers. But the distance between Earth and the moon is only 300,000 kilometers. It's, just a third of a million. And there's 150 million, to get to the sun. So we're talking a tiny fraction. It wouldn't even show up in a figure that showed the orbit of Earth around the sun. Okay, another question. Planets A and B have the same semi-major axis. Planet A has a much larger, there's an extra than there. So planet A has a much larger eccentricity than planet B. Which planet has a shorter perihelion distance? Think about what it means to have the perihelion when you're closest. Would you get closer if you were more eccentric or less eccentric? And to help kind of like think about those two black dots and how if the eccentricity goes down, the two black dots approach each other. But in this case, we're keeping the semi-major axis, which is the blue line, we're keeping that constant. That can't change because we're comparing two planets that have the same value. And then what would happen to the perihelion? All right. Okay, cool. Some some planet A, which is one, some planet B, a lot of three, which is the same. Okay, cool. So there you go. Those of you that said A, you were right. And the way I can best explain that is just to again refer to this figure. And if I have, I'll try to do this like this. So if I draw a quick line, okay, so I'm gonna have a orbit that's circular. Okay, so imagine this. This is a very low eccentricity orbit. I'm just going over it again, to make it a little bit thicker. Okay, so this more or less circular path would be the path of planet B. Because remember, planet B is the one with less eccentricity. And I think it's really easy to mix it up based on the phrasing here, let alone the extra, than the typo. But anyway, so that I know that can happen. But planet B is the one with less eccentricity. So it's closer to a perfect circle. So that's the red line that I just drew. So in that case, this blue line, which is the semi-major axis, well, it basically represents the radius, right? Because the semi-major axis becomes the radius when your eccentricity becomes zero, right? Special case. So, well, in that case, when you're at perihelion, you're as close as you're ever going to be to the sun, the thing you're orbiting. Well, if your orbit looks like this red circle and the two foci have basically become a single point at the center, then the closest you're ever going to be to the sun is the whole blue line because you'll just always be that far away. So your perihelion will be essentially will equal your aphelion, right? If your eccentricity is zero. Well, okay, so that would be our less eccentric orbit. But then planet A, which has the more eccentric orbit, that's like the actual picture. That's like the black ellipse. Well, there, the aphelion is the distance between the foci, let's call it the foci on the left, and the edge of the ellipse. Well, that's clearly shorter than the whole blue line. By the looks of it, it's about half the blue line. So then this would be your perihelion distance for the more eccentric orbit. And just to clarify, the aphelion for that more eccentric orbit would be this line, right? So quite long, see? So there's a big difference between the two. But for the purpose of the correct answer, the perihelion is much shorter. You're much closer. All right. Hopefully that makes it obvious or it makes it more clear. All right. This is showing the explanation. Okay. Maybe with a better circle than mine. Okay, so there you go. And this is kind of cool because it's not a perfect circle, right? But you can clearly see, right? Much shorter perihelion for the more eccentric orbit. Longer perihelion, not as close for the less eccentric. And there's a comparison. All right. Okay. So that's it for Kepler's first law. It actually took more slides than the next two laws will, even though in a sense it's the simplest. And that's because we had to get so many definitions of ellipses out of the way. Really had to define what an ellipse was. So with Kepler's second law, technically, mathematically, it's got more going on, but we've already laid the groundwork of an ellipse so we can build on it. So here it is. The law states, at least one way to state it, is that a line between a star and a planet sweeps out equal, you know, equal area. So sweeps out in equal time. Okay, so the line will sweep out the same amount of area in the same amount of time. But what this looks like is this. So imagine that you had a difference, and we're going to be going from, so we got January 3rd, December 1st. So we're going, it's interesting because they put the arrows going in the clockwise direction, but the dates are going in the counterclockwise direction, which is correct. So the arrows should face the other way. Someone forgot that orbits are counterclockwise, but then someone else remembered, right? So this is some sort of teamwork creating the figure. So these arrows are incorrect. They should point the opposite way. So if we're going from December 1st, not that it matters for the law, but that is a relevant point. So if we're going from December 1st to January 3rd, all right, so that's the amount of time. So however many days from December 1st to January 3rd, right? So third, well, 31 days if we include December 1st, and then we have another 3 days. So 34 days to go from that point to that point. Then there's a certain amount of area enclosed by this wedge, right? This sort of, you know, lopsided wedge as a area. That's the shaded green area. All right. Well, then if we compare to a different amount of time on a different portion of the orbit, then we're going to get the same size wedge. But first, let's make our wedge a little bit more symmetric looking and have it go all the way to January 31st. Right, so now we have this whole kind of side of the ellipse. And then let's go over to a whole other part of the year. And it seems like we're kind of referring to Earth here, right? But of course, our orbit is much more eccentric than Earth's orbit truly is. Still, gets the point across. So now we go over to June 1st, and then we're going to compare a point that is, a certain number of days later, about equivalent, so about a month and a day, although the first one was a month and 2 days. But then we get to a point that is exactly 60, I believe, if we're thinking about which days have 30 months, either 60 or 61. But the point being is that this is the same number of days for both wedges, the same amount of time. Okay. So same amount of time is covered. The same portion of the orbital period is covered for both sections of the elliptical orbit for both wedges. And although their shapes are really different, with the green wedge being short and wide, and the yellow wedge being long and somewhat narrow, their areas are the same. So the shaded yellow area and the shaded green area are equal. And that is what Kepler's second law states, is that those areas are essentially conserved. They have to be the same. The area swept out by an orbit in a certain amount of time is always equal. Right? So same area. This concept is, in fact, in modern physics, conservation of angular momentum. Not responsible to know that, but that's what it's kind of been replaced with, and that's not wasn't known to Kepler at the time, but that's what's going on here. Is the angular momentum is being conserved. What's really is important is the consequence that this has on the speed of the planet. And it would be its speed relative to the sun, the thing it's orbiting. Okay. So when is Earth moving faster through space? In the period from December to January, the period from June to August, or does it always have the same speed? But based off of Kepler's second law and this idea that these two areas have to be equal to each other, despite their different proportions, what does that tell us about the speed? Okay. Cool, cool. Yeah, okay. It's like everybody gets it. I'm glad. Because you just that's the answer. Because when you look at it, you just need to look at how far you've gone. So, if Earth is traveling from this black dot at December 1st to this next one at January 31st in 2 months, well, that's a long path, right? So it has to cover that whole path in 2 months. But then come summertime, it has to cover a much shorter path. I mean, visibly shorter in the same amount of time. So what that means is that planets always move faster when they're at perihelion. They pick up speed. It's like a roller coaster that's moving faster when it's reached the bottom of a drop. And in that regard, it's related to conservation of energy. And it actually totally is. So what's so interesting about this law is that it ended up being a precursor of some of the big conservation laws, which are very important to modern physics. The one I mentioned a moment ago, angular momentum, and also conservation of potential and kinetic energy. All right, so that was it for Kepler's second law. What you mostly care about is that result, the fact that planets go faster when they're at perihelion and slower when they're at aphelion, right? And that's all because of a conserved quantity, if you kind of want to have a tie-in, but mostly you care about the consequence. Right? Just get rid of something real fast. Okay, so third law, this is the last of the three. What this law does is it allows us to relate the period of an orbit to its distance from the sun, specifically to its semi-major axis. And the relationship between those two quantities is the square of the period and the cube of the semi-major axis. And this little symbol, if you haven't seen it, means proportional. So it's not an equal sign because the period is measured in seconds. Semi-major axis is measured in meters because one is a measure of time, the other is a measure of distance. You can't have seconds squared equals meters cubed because seconds don't equal meters, right? Let alone seconds squared equals meter cubed. You have to have the same units on either side of an equation, always. So since there isn't the same units on both sides, we're obviously missing some constants, we're missing some other quantities, but despite that, it's still a proportionality. So even without the correct, values, we can still state that this is true as a ratio, as a proportionality, right? And in fact, you can write it as a ratio. You could divide both sides by the semi-major axis cubed. So divide both sides by a cubed, and you'd have p squared over a cubed is proportional to 1. In other words, it's a fixed value. The ratio of the square of the period over the cube of the semi-major axis is a constant. All right. And what's great about this is that if you're interested in a bunch of bodies, planets, because we call them like, like celestial bodies is a real general term. So if you have a bunch of planets that are orbiting the same star, like the 8 planets that orbit the sun, well, then you can use this proportionality to relate one to the other. Because it turns out that the actual missing constants in here, the missing values that would make it an equation, are shared by all the planets. So we can get the correct values as long as we're only talking about, you know, planets orbiting the sun. You cannot go from planets orbiting the sun to moons of Jupiter orbiting Jupiter because then you have a different body being orbited and there you couldn't, use the period of one to find the semi-major axis of the other. So you have to kind of stick within the same system and you can use Kepler's third law exactly as written. We also will see a version of Kepler's third law where we do introduce the constants, and that's called Newton's version. And it was, in fact, Newton that added to Kepler's law and you made it an equation. But so far, this is a proportionality. All right, so all of that is great, but you probably care more about what does it really tell us, right? Well, what it tells us is that as you go further from the sun, right? So as A gets bigger and bigger, so you have your more distant planets, the period is going to grow, and it's going to grow at a rate that it's going to grow at a faster rate than A. Because whatever quantity, whatever number you have for the period, you need to be able to square it and equal your new value of semi-major axis cubed. Well, if you need to square something and have it be equal or at least proportional to another number cubed, the number you're squaring has to be bigger because, you're doing a smaller operation with it. So what that tells us is that the period grows faster than the semi-major axis. In other words, if you have a planet that's twice as far from the sun, its period isn't twice as long. It's going to be longer than that. It's going to be more than twice as long. And by period, I mean it's year, right? So if we talk about the Jupiter year, which is just the time it takes Jupiter to orbit the sun, right? The Neptune year, and so on. Well, those will be greater as a multiplier than the difference in the distance from the sun. And we pointed out here at the bottom that the period to use this as a really effective proportionality, we keep the period in Earth years and the axis in astronomical units. All right. So check the time. All right. So we're not going to get into Newton's universal law of gravitation or his other laws in the next 10 minutes. So I just want to do one last note about Kepler's third law. So let's plug in a number here. So let's put in P. All right. So I'm going to have P equals 1 year. Okay. And this would be for Earth. All right. And then I'm going to have the P, and I'll put an E here for Earth. And then let's think about what would be a good one. Let's have um, Jupiter. All right. So then I'm going to say, what is the orbital period of Jupiter? I'll put that as a question mark. And then over here, I'm going to specify, and it's kind of weird. I'm putting the P's on one side and the A's on the other, but we'll do it like that. And so over here, I'm going to put the semi-major axis of Earth. So A with an E for Earth. And that's just going to be 1 again, because we're using these units that are specialized for Earth, where, 1 year is our comparative period, and one astronomical unit is our comparative distance from the sun, our semi-major axis. And then I'm going to give you the semi-major axis for Jupiter. I believe is either 10 or 11. Let's double check on my table of values here. No, I was thinking it's Saturn that's closer to 10. Jupiter's just 5.2. All right, so we'll do 5.2 AU. Okay, so now, as your last task of the day, I want you to do math. I want you to find the period of Jupiter based off of this information and Kepler's third law. What must be the orbital period of Jupiter? Just think that you would plug in and solve for that A value. Because you can directly plug in. That's the advantage of using AU in 1 year, because 1 squared actually equals 1 cubed. So that means if I plug in 5.2 cubed, I can directly solve for P as long as I get rid of that square, which would be taking the square root, right? Yep, and spend like 2 minutes, two more minutes on this, and then you can wrap it up. Is anyone thinking of plugging in the 5.2, cubing it, and then taking the square root of it? Let's see. We got something in the chat. Okay. What number did you get, Alara? Okay, cool. I see it now. I see Fiore's. Okay, cool. I missed that one. So 11.86. Nice. You were so fast, I missed it. So yep. Let me double check. I think that is right. So 5.2 cubed. And then, you could do it all in one step, but if you wanted, you could just separately get that. That gives you 140 as the cube of the semi-major axis. And then you just take the square root of that quantity. Try not to round too much. Yep. 11.85. Awesome. And actually, yeah, it does round to 11.86. Nice. So then we'll stick with there was no particular number of sig figs. So sure. I'll just write it right here real fast. 11.86 years. Nice. All right. So I'll show one more thing in case someone's thinking, well, what are the steps again? So you'd be like, your P would just be, and this I'm writing as an equation because we're just sticking to this comparison between things that all orbit the same body, and we're sticking with all using these units, okay, of astronomical units in years. So in this way, we can not worry about the constants. And then we just put in the 5.2, and then it would be cubed. And then to get P by itself, the whole thing is inside a square root. That'd be one way to write it all in one step. That gives you 11.86. And then just the last thing I'll point out is that that's what I meant by one goes up faster than the other, right? Because our semi-major axis was 5 times bigger for Jupiter compared to Earth, but the period is almost 12 times bigger. So as you get further and further out, there's this more dramatic increase in period length, the actual time to orbit, as compared to distance from the sun. And the one thing that I find is really easy as an easy mistake to make is to think the opposite. Because when you look at the equation, p is squared, but a is cubed. You might think, well, then, a should be the thing that grows faster. Is it's cubed? Shouldn't a grow faster? Well, no, it's the opposite. It's and I tried to explain that a minute ago. It's the thing that's being, only squared that has to grow faster because they're equal to each other. All right. So that wraps up Kepler's third law and our progress through chapter three. We'll definitely finish chapter three tomorrow. Look ahead if you want to be prepared because we'll go ahead and take a chapter three quiz. But it won't be as early. We'll probably take it sometime in the second hour. But that's the plan, and we're on track. And yeah, you could get a math question like this, but only with numbers that work out nicely and probably more like interpreting a graph. You would not get one where you have to actually crunch numbers and you get decimals. But there will be one in the homework like that. But you won't get one that requires actual calculation on the quiz. It'd be more like just identifying which one is which on a graph or something similar. All right. Well, everybody, have a great rest of your day. Maybe you'll be hearing from me as I respond to messages and be on the lookout for that corrected gradebook. Hey, that's no. And stop our recording over here on Zoom and save it.